Hello again. This is chapter 4 again. This is the last section. So let us get started. I hope you're doing fine. So we are going to talk about this last section of chapter 7 on modeling with trigonometric equations. Now, trigonometric equations and application problems look kind of like these two right here. So we have sine and cosine, and they're called sinusoidal equations. So the difference here is that we're going to use these forms here. Why? Because remember, when something goes in a has a circular motion, it has angular velocity. So the angular velocity is how much angle per unit of time. And if you put a 1 here and cross multiply, you get theta equals to omega t. So omega is angular velocity. So instead of writing theta here or here, we can just put omega x or omega t. It's like if you go 50 miles per hour for, let's say, 2 hours, then the hours go away, then you have gone 100 miles. So if this thing goes around maybe 3 pi per minute for, let's say, 2 minutes, then the minutes go away, so we have 6 pi. So that means we cover 6 pi radian. So that's 2 pi, 4 pi, 6 pi, right? So that's the idea of using omega t instead of angle. That is going to be very useful. All right, so the A, B, C, and D, they play the same role as before. We talked about these already. Absolute value of A is the amplitude, and the amplitude is, if you look at sine, would be this distance or this distance, and that is just max minus min divided by 2. And the D, which is this line right here, y equals to D, is max plus min divided by 2. Is the number in the middle of max and min, so it would be max plus min divided by 2. And C over B is still phase shift. Don't get confused with these signs. If you add, you go to the left. If you subtract, you go to the right. So we put a minus here to indicate that C over B is the phase shift, whatever the sign of that is. So if that turns out to be like negative pi, then that would be negative. So C over B is negative. That means this would be negative. So that's the idea. All right, so let's talk about 4 structures that are used in application problems. So if we want to write an application problem in terms of sine or cosine, we use these structures. See, that's one cycle of sine, and this is also one cycle of sine. Notice that sine starts from average, goes up to max, comes back to average, goes to min, then comes back to average. Whether sine is flipped over the x-axis or not, we always start from average and then go down to min and go back to max and then the average. But cosine, on the other hand, either you start from max, right, and then go back to max, or you start from min and then you go back to min in one cycle. So these structures are used in application problems. And I'm gonna review these one more time a little bit. Here's an example, y equals to negative 3 sine 2x plus pi over 2. So here we know the amplitude is 3, right? Amplitude is going to be 3 right here. and the period is 2 pi divided by 2, which is pi, and the middle line D here is 0, and our phase shift is going to be C over B. C is actually, remember, this is a minus, so this is C. C would be negative pi over 2, right, over 2, so which is negative pi over 4. So the rectangle that we built, the midline would be at 0, right? This midline is at 0, and then we go up. How many? Well, where is A? 3. We go up 3, and we go down 3, right? That's that. Now, we don't know horizontally where to start unless you find what? The phase shift. So that number right there is, this number right here on the x-axis is negative pi over 4. And the period is pi, right? So negative pi over 4, we have to add to it pi. Now pi is 4 pi over 4 plus negative 1 pi over 4 is 3 pi over 4. So that number on the other side of the rectangle is 3 pi over 4. So you see we got the rectangle, and we know this is a negative here. Since that's a negative number, that means this is sine but is flipped, right? So that's the graph. We could also do this by graphing the key points, and I'm going to review that as well quickly. So how do we do that? Well, we can think of the 5 points. Where are the 5 key points? You see, ordinary cosine, of course, has 5 points, but the ordinary cosine looks like this, right? So that's the rectangle. But we don't have to think about this and then transform them. We could just, get the first point. What's the first point? The first point would be what? The first point is when, let me erase that. So the 5 key points are going to be, looks like I have to erase this here too. So I did that one more time for you, but this is another example of doing this. So negative 4 cosine pi x, this right here. Again, amplitude is 4. B is pi, so the period is 2 pi over pi, which is 2. Amplitude is 4. The middle one is 0, D. So again, we start from 0. We go up 4 and down 4. And I just noticed this has to be 8, not 6. So this distance is 8, and the period is 2. Now what do we start with on the x-axis? We know in terms of y, this is 0, but what about in terms of x? Well, in terms of x, that's our phase shift, and the phase shift is 0. So we start from 0 here and also on the x-axis. So if you start from 0 on the x-axis and the period is 2, so you go to 2. So this number right here is 2. So you see you go from 0 to 2 and from negative 4 to 4, and we got the rectangle. And then we know this is a cosine, but it's flipped. How do we know? Let me see, this has to be 8. So it's flipped. That means what? This is negative, this number. So it's cosine flipped over the x-axis, and we can graph it. You could also think of 5 points and graph them, right? So you can say, okay, this is a function. What's the left edge point, this point? Well, it starts at point 0 and negative 4. So if we put x equal to 0 here, we get cosine 0 is 1 times negative 4 is negative 4. So that's 0, negative 4 right there. And then we know this one, it's 0. That right edge, this point right here, would be x value 0 plus the period. That's the x coordinate. Period is 2, so that was 0 plus 2 is 2, right? And the y value would be, if you put a 2 here, cosine 2 pi is 1 again. 1 times negative 4 is negative 4. So we get this point. Okay? And the top and the bottom of edges, of course, we know there are d plus the amplitude and d minus the amplitude, right? And then we can find the x coordinates in the middle by dividing the period into 4. So period divided by 4 is 0.5. So each of these is 0.5. So from 0 here, and then this is 0.5, this is 1, this is 1.5, this is 2 on the x-axis. And we know the structure of, one cycle of cosine. All right, so let's move on. Now, this is the main thing we want to do in this chapter. Applications like this. We are given a bunch of numbers here from January to December, and these are average temperature for some small town, right? So in January is that, in February is that, and so forth. So we're gonna assume we're gonna write a sine function for this periodic behavior of temperature. So we're gonna assume that January as number 1, and this is 2, 3, 4, and so forth, all the way to 12. So 13 would be again the next January, right? And so we're going to look at what these numbers A, B, C, D have to be. Now we can find A. A is the middle number. So middle number is the average of is the maximum minus the minimum divided by 2, right? I mean maximum plus the minimum divided by 2, plus the min divided by 2. So D is going to be the maximum here is 69, plus the minimum is 42.5. If you look at it, you see. So we add them, divide by 2, we get 55.8. So the number in the middle here, the midline, that number D, is 55.8. Now, this A here, what is that? Well, that's the amplitude. What is the amplitude? Amplitude is maximum minus the minimum divided by 2. So 13.25. That means from, we're going to call that 13.5, right? And then, again, we don't know what B and C are yet, but we know this has to be 13.3, right? So that's the amplitude. We still don't know whether it's max or min. We still don't know whether it's positive or negative, but we're going to find out in a second. Okay, so we put that A here to be 13.3, and D is 55.8. Now, we use X and Y values of the first month to find C. So we use 1 and 42.5 for Y. This is X, this is Y. So Y here would be 42.5, and then X would be 1. So from here we get 42.5 equals 13.3 sine, that plus 55.8. Now, we also know that the period, right? What is B here? Well, let's see. The period here is 12 because it's 12 months, right? So it's 12. After 12, so if the unit of time is 1 day, right? 1 month. So 1 is the first month, 2 is the second month, and so forth. So that means the period is 12, and we know 2 pi divided by B is the period. So if you cross multiply and find B, B is pi over 6. So that's where we got B from. So we just have to find C, and to find C, we get the first point, 42.5 for Y, and then 1 for X. This, if you follow it, you see that we end up with sine of that equals to negative 1. So so what do we get? We get, if we take sine inverse of both sides, get rid of the sign. So we get pi over 6 minus c equals sine inverse of negative 1. And we know sine inverse of negative 1 in the region that sine inverse is defined, right, is only one number, and that's negative pi over 2. So this has to be negative pi over 2, so we solve for c here. It has to be 2 pi over 3. So we got a complete picture of this, right? And notice that we start with average, so it's a sine graph, right? We use the sine graph. And so it's, not with average. We start with the minimum, right? We start with the minimum here, right there, 42.5 is the minimum. And then we go to average, right? And then we go to max and then come back to average and go to the min again, and then January starts, next January. All right, so that is the function. Since we want sine, we have a shift, of course, right? There is a shift in sine, and the shift is 2 pi over 3. All right, so basically what we have here is a sine function, right? We have to start January somewhere. So where do we start January at? At 1, right? Right there. So if we use this shift at 1, we end up with this number, right? Obviously, you might say, well, sine looks like this, but that is if it's not shifted. We start at the average. Oops. We start at the average if you're not shifted. But if you shift sine, then you can start from here, you can start from anywhere if you shift it. Okay, so there is a shift of 2 pi over 3 to the right, right? And we start at 1. All right, so that is actually, if you graph it with a computer calculator, this is the graph of sine. You see, this is, of course, continues this way, and, it's like that, but we don't want that. We want to start from here. So C determines where on the unit circle, where do you start to actually graph this, right? So we could have started with a different number. For example, here, different value for C we could have found. So we could have said, okay, let this be equal to 3 pi over 2, because that 3 pi over 2 sine is also negative 1, right? And then find difference C. And if you find difference C, since C is negative 8 pi over 6, and this has to be a minus, minus times minus is plus. So we get this. It's the same function, but different what? Different C. But I graph both of them here, you see they match. The difference between this one and this one, I explain here. You see, it says at x equal to 1, 1 here is time, it's not angle, right? 1 is time. The angle is actually pi over 6 plus that. That's where you start, right? So at 1, the angle would be 3 pi over 2 for this function. For the blue function, if x equal to 1, then this argument is negative pi over 2. So over here, we start with negative pi over 2, and then we go around the unit circle to graph this. But in this one, right, we start with 3 pi over 2. Oops. So we start with 3 pi over 2, positive 3 pi over 2, and graph this, which is the same thing, right? It's the same thing. But the values are the same, you see. We still get 42.5, which is the min. So at 1, we start with min. Now, these kind of problems, we could also do it with a calculator. So let me bring my calculator. All right. So if you put the numbers in L1 and L2 in the calculator, and I have two of them, let me get rid of one. So you go to Stat, you go to Edit, and you put these numbers in L1 and L2. Then you can go to, you can actually graph these points. So let me go to y equal to and get rid of all of these numbers here. And then go to Stat, Plot, get the first one, turn it on, and then we want the scatter plot of these points. And the x is in L1, the y is in L2, right? I'm talking about the same table, right? We're talking about the same, let me see, the same table that we're talking about, this table right here. I put 1 through 12 and then these numbers, right, as you see right here, right? So I'm going to graph them with a stat plot, and I'm going to go to zoom 9 to graph them. You see? Now, calculator can find a function for you that goes through these points, and this is sinusoidal function. The way it works is you go to Stat, Calculate, and then you go to almost the last one is called sinusoidal regression. You take that one. Let me Stat, Calculate, sinusoidal regression, and then you put L1 comma L2 in front of it, right after it, and it takes a few seconds. You see, it found a sine bx plus c plus d for you. These are A, B, C, Ds. Now, since there are so many decimal places, I'm going to go to y equals to and get this from memory of the calculator and put it in y equals to and graph it. So I go to y equals to and go to Variables, Statistics, Equation. The first one is regression equation. There, it puts it there for me. You see, it has that form, some number times sine of some number times x plus some number plus some number. That's D right there. But it has many decimal places. So I'm going to graph now. You see, calculator found a model for us. And that's how we do these things actually with computers and calculators. So here I have the one that we did by hand and the one that the calculator found, which are not exactly the same because calculator uses calculus and probably a better model than ours. So the blue one is the one we found with by hand, and the red one is the calculator one. Okay? All right. So now I want to talk about simple harmonic motion. Simple harmonic motion is a periodic motion, right? They cycle through their periods, right? Here's important, no outside interference. For example, if we have a spring and there is a weight connected to it, and this is the wall, and here's, let's say you set it on a table, we assume that if we pull this way and let it go, this is going to oscillate like that, right? And in simple harmonic motion, we assume that this thing would oscillate without any interference of any other forces, including friction. No friction, no gravity, nothing. Only the force of the spring is involved here. If that's the case, then if you pull a string and let it go, it is going to oscillate like that. And we can write an equation for that. And the equation is usually either cosine or sine. depending on how you start, whether you stretch it or you compress it and let it go. Okay? In either case, we can use one of these equations to write equation for the simple harmonic motion. So let me do an example. Here is an example. If we assume this is a simple harmonic motion, it says for the given function, find the maximum displacement of the object, find the period or the time required for one vibration, and find the frequency and sketch the graph. Now, frequency is 1 over period. That's what frequency is. So period is 2 pi over omega. So frequency is omega over 2 pi. Is a reciprocal of it. So here, well, let's see. The period is 2 pi over omega, so it's 2 pi over 3. The frequency is 1 over period, so it's 3 over 2 pi. The maximum displacement is actually the amplitude. That means, let's say this is a spring and a weight. So maximum displacement means how much from some reference point, let's say from here, how much displacement do we have? The maximum would be from some reference point. Let's say we leave this spring over here. At the moment is at this point. Now let's say we stretch it all the way here and then let it go. So that's the maximum displacement. And that is the amplitude of this function, which is 5. So maximum displacement is 5. Okay, and for that blue one. For the red one, maximum displacement again is 5, but the period is 2 pi divided by pi over 2, which is 4. And the frequency is 1 over 4. And these are the graphs, and you know that already. All right, so here's an example. Spring measuring 10 inches in natural length is compressed by 5 inches and released. So this spring used to be over here at 10. So we compress it all the way to 5 inches, right? We assume that, let's say this is 5, okay? So we compress it, let it go. What happens? Well, if we assume there is no friction, no gravity, nothing, this is going to just go back and forth, right? So now at time 0, the displacement is the minimum. It's 5 units displacement as the minimum because we compressed it. So we're looking for a structure that starts from a minimum. So it has to be a cosine. And also, cosine starts from the max or from the min, right? And we want flipped cosine. So that's what we need. So we know this number has to be negative, right? What is that number? Well, first of all, we know D has to be 10 because naturally this thing is what is at 10, is right here, right? Naturally, this is spring. It's supposed to be here. We compress it 5 to 5 to number 5 here is at number 10. So naturally it's at 10. That means eventually, before we moved it, it was at average, right? So that is 10. So D is 10, right? Displacement. Now, A is negative 5. Why? Because, as I said, that would be the min, so we have to pick the flipped cosine. So that's negative 5. And since we start at 0, we let C be 0. All right, now frequency we are given. The frequency is 0.5. What does that mean? That means omega over 2 pi is 0.5. So omega is 2 pi times 0.5, which is pi. So that's pi. So the equation for this is that right here. And you see right here, think of this as y-axis. So we measure the displacement on the y-axis. Of course, y-axis is here, but we assume this is y-axis and there are no other forces involved. So this is going to start from 5, right? And then we let it go. It goes past 10, and it's going to go to what? Go to 15, right here, right? Because what? Because of the force of the spring. So this is going to go to 15, then it's going to come back. So it goes to that, and then comes back to 5, and then goes back to 15, and comes back. We assume there is no friction, so it's going to do that forever. So we start at 5, as you see on the y-axis, and then we go to past the average, which is 10 right here, and then go to 15, back to 5, to 10, and then back to 5. And assume this continues forever. Right? So that's simple harmonic motion. Now, of course, that's not real. In real world, that doesn't happen. So in real world, what happens is that this comes over here, doesn't come all the way to 15. It comes to somewhere over here, and then maybe over here, and then comes back, doesn't go all the way to 5. It's going to like stop here, kind of like that, and then it's going to come back even, then it's going to come back, and it's going to come back, and then it's going to stop. That's called damped harmonic motion. Damped harmonic motion. So what happens is that you see the amplitude that usually is just a here, instead of a is a function. And that function, as you remember, this is an exponential function, and it looks like a decreasing function like that. So the amplitude, think of sine going up and down like that, but as time passes, the amplitude gets smaller and smaller. See? Like that. So it's the same sine function with the same period, everything, except the amplitude keeps getting smaller and smaller. In fact, when you do that, it turns out that this function is going to be like sine function that's stuck between this function and its negative. See, that's that function, and this is right here is the negative of that function. So sine function is stuck between these two. So that's the idea of damped harmonic motion. So here's an example. 10 times e to negative 1/5 t sine 2t. Now this number right here, c, is actually a damping factor. That determines how fast the amplitude is going to go to 0. All right? And notice that there's a negative here. That makes it a decreasing function. Okay? So, model the equations that fit the two scenarios and use a graphing utility to graph the functions. Two mass spring systems exhibit damped harmonic motion at a frequency of 0.5 cycles per second. Both have initial displacement of 10. The first has a damping factor of 0.5, and the second one has a damping factor of 0.1. So basically, we have formulas, right? So we use the formula. We are given the maximum displacement is 10, and we are given that c is either 0.5 or 0.1. So there are two systems. This is with 0.5 and this is with 0.1. And the frequency is 0.5, so that means omega over 2 pi is 0.5, so omega is pi. So omega here is pi, and we are done. These are the models. Now, when you graph these, you're going to realize that since this has a larger damping factor, this is going to go down quicker, the amplitude. And I have them graphed over here so you can see. You see, this one right around 12 is already going down. But this one keeps its height up to about 45 or something, right? And then the amplitude gets smaller and smaller because the damping factor of this one is smaller, as you see. So the treatment of these, complete treatment would be in calculus or in engineering math. But here I'm just mentioning them because they're important functions in application problems. Okay, so here is an example with damping. A spring measuring 10 inches in natural length is compressed by 5 inches. It's just like the example that we did. But this time we're going to take friction into account. So the friction causes this to lose 30% of its displacement. So if you let it go here, it's not going to go to 15, but it's going to go to 70% of 15 because it loses 30%. So it's find an equation that models the position of the spring t seconds after being released. So the spring's amplitude of oscillation is initially 5 inches and it decreases by 30%. So basically the amplitude is going to be 5 first. Next time is going to be 30% less. That means 70%. And then next time is going to be 70% of that. And then next time will 70% of that, and so forth, right? So basically, A of t is going to be 5 times 0.70 to the tth power. And now we like to write it in terms of E, of course. Remember, we like to use E. So what do? We convert this to E. And this is a little thing from algebra. We want 5.7 to the t to be 5e to ct. Now, compare this to that. It looks like if we write this as something to tth power, which is e to c to t, if you have two exponents, you have to multiply them, right? So compare this to that. It looks like we want e to c to be 0.70, right? So e to c has to be 0.70, and this is like a simple exponential equation. Take ln of both sides. Ln, you take ln of e to c, you get c, right? So c equals to ln 0.7. ln 0.7 is about negative 0.357. So our damping function is going to be what? That function, right? Now we're going to think about whether we use cosine or sine, right? That's the damping function. Well, here, since we are starting at what? Starting at minimum, we're going to use a cosine function, right? Because we compress it, so we start from minimum. We're going to use cosine omega t, right? And since there's a natural length of the natural length is 10, right? Then the average, the middle would be 10, right? We moved it from 10, this is 10 right here, so we compressed it from 10 here. So it's going to come back here, but it's not going to go to 15. Then it's going to do this, and as you see it here, and it's going to stop eventually. So so what is omega? Well, we know again we know that period is 3 because we were given that. Right here it says oscillates once every 3 seconds. So the period is oscillates once every 3 seconds. That means the period is 3 seconds. So 2 pi over omega is period. So omega has to be 2 pi over 3. And we have the amplitude function. And we are done. This is the graph. See, we start from 5. And we go to not to 15, but it goes to about that number, which is 13 something. Comes back, but doesn't go to 5. It goes to like something number right there. Right? And then goes back a little bit lower than that, and then a little bit higher than that, and eventually stops. All right? All right, and again, you think of this as y-axis, and we are writing displacement right here. We're representing it here. All right, now the last thing I want to do, I want to show you in general in the notes. If you click on this, you can go to the audio is going to be a little off, but you see here is the damping function, and we can change, we can change this omega here is a sine function, and this damping function doesn't have to be e to x, it could be anything. Let me just put x there, and you see we have this function is oscillating between x and negative x, or it could be x squared. You see is oscillating between x squared and negative x squared, and it could be any function. You could be another maybe sine function, right? Let's make it another sine function. You see is oscillating between what? Between sine function oscillating within a sine and negative sine function, as you see there. Any function, you can put any function there, and so I'm going to put one more and then we stop, and that's tangent function. Let's see if it works with tangent. No, let me do it. Tangent. Yeah, here we go. So sine is oscillating within two tangent functions. Again, as I said, the best way to deal with this is using calculus, but I'm going to stop the video at this point and go over here and say bye to you. Okay, so see you in the next video. Take care.